Welcome, everybody. Thank you for being here at this different time tonight or morning. Today, we are very excited to have Jong-Yoon Choi present their work, Continual Learning in Systems Perspective. Jong-Yoon is an associate professor, I believe, still at Yonsei University in Seoul, South Korea.
Right. Mhm.
We had him on last spring, if you remember. He discussed fantastic works in practical continual learning settings, so we were very excited that he accepted our invitation to return this fall so we can hear more about you and your lab's recent work. So without further ado, please go ahead and take it away. I will apologize, we're having a small screen difficulty with Microsoft Teams, but I'm happy to announce that starting January 2023, we are going to abandon Microsoft Teams for these seminars.
Okay.
So, go ahead and take it away. Thank you.
Yeah. Thank you very much for the kind introduction, James. So my name is Jonghyun, and today I'm talking about the continual learning and systems perspective, with a brief recap of my previous work on the practical scenarios of continual learning that I have delivered in April or May in 2022. Right, so to recap, we have this taxonomy of the class incremental learning or the continual learning in general. And this taxonomy is made by the Tin Tuitula and her groups. And we have these three different categories of continual learning methods. The first one is the replay-based one, and the second one is regularization-based one, and the last one is the parameter isolation methods. So the first replay-based method is basically recap of the previously given data in a form that we are using the data exactly. That is called rehearsal method, or we can use the pseudo rehearsal by using a generative model trained with the previous data, or the constrained model that is getting or storing the gradients or some embedding from the previous data and use it for somehow for training the next stages model. So they are basically the replay based method because we are using anyway the previous data as information. And the second one is the regularization method. And we can also categorize them further by prior focused and the data focused. The prior focused is relying on the human designed prior to regularize the training, the current model, as opposed to we have the previously learned model that we can use as a prior, but we are using just human design prior for learning a new model. And the data focused regularization method is the a method to use the previously learned model to regularize the current training model. So that is having lots of famous models like LFW or DMC or sorry, the LFL, and also the prior focus we have this famous EWC and its variants that is Riemannian work. Yeah, and the third last category is the parameter isolation method. The idea behind that is basically not harming the previously learned parameters, but updating or learning a new parameters. Then use this new parameter that is not touching the previously learned parameters and merge them somehow in a fixed network constraint or the dynamic architecture constraint. That means we are adding additional capacity to the given model so that we are increasingly having larger models as the task is proceeding. So over these three methods, the replay-based methods are having the highlights because it's very simple and it maintains the accuracy over time pretty well compared to the other two methods. So I'm also focusing on this replay-based method, and specifically I'm focusing on this rehearsal-based method that uses the episodic memory over the course of time. And the spring talk, I have talked about these many different scenarios for the continual learning, and I claim that we have to worry about whether we are going in the right direction or not by uh, addressing the real world-like task as opposed to the lab-like task, right? So in the spring talk, I was comparing the disjoint setup and blurry setup and online and offline setup. So the disjoint and blurry setups are uh, having the task configuration that has the overlapping classes among the tasks, and that is called the blurry setup. And if there's no overlapping classes over the task, then we call this class incremental learning setup as a disjoint. And disjoint setup is usually regarded as more challenging for the forgetting because you don't have any new, you don't have any information for the previously given task, right? Or the previously given classes. But the blurry setup, in contrast, is suffering from less forgetting, but it's more realistic setup, and people try to use this setup over more and more over the disjoint setup because it's more realistic. And the online and offline setup is having the differences of looking at the data in how many times we are looking at the data for the newly given cases. So the online learning, we are only constraining the model to look at the newly given data once, but the offline setup, we are allowing the model to train or the updates by looking at the newly given data over and over again. So the online setup is more realistic because in a continual learning, they are usually regarded as the setup for the AI deployed to the small devices or the robotics uh, kind of agent, then we don't have a luxury to look at the data over and over again to update the model, but we are looking at once and just update it and just go to the next stream of the data. So that is the more realistic setup, but it's more challenging because you don't have much of time to update your model because you don't have much time to look at the data. So I was more interested in more realistic setup. So I tackled this blurry and online setup mainly by posing a new method to managing the episodic memories. And as I said before in the previous slides, continual learning scenario would be more necessary in the user and devices. So we consider the resource constraint scenarios like the limited episodic memory and the limited model size. But now we are not talking about the limited model size, uh, but we are talking about the limited episodic memory usually, but we are not talking about the limited model size yet. So I think this is a very good research avenue for the most of the people that we need to go to the small or compressed model to tackle this real world continual learning scenarios. Yeah. So if I depict the scenarios that we are having for updating the model over and over again with the streamed data with the memory, we can think of this data is given to the model and the memory is used to store the small portion of the previously given data, and we update the model continuously and also update the memory over time. And we assume that this data is annotated by a human annotator like somehow. And we don't have a luxury to look at this data more and over and over again, but we are having just only one's uh, data looking at, and we call this as an online setup, and we mainly focus on that setup. Yep. So to recap, in the spring talk, I was talking about my idea to manage the episodic memory by diversifying the data in the episodic memory. We call it rainbow memory. So by looking at the confidence of currently trained model of newly given data by transforming the data itself and then see the fluctuation or the variance of the confidence of this transformed data by using a bunch of different transformation, like occluded the half of the image or the rotated or the color jitter and things like that, and see how much the confidence is fluctuated. And if the confidence is fluctuated a lot, then means this image is not, or this sample is not learned thoroughly by the currently trained model. So we think that this is pretty uncertain sample for the network. And if the confidence are consistent over the transformation, we think that this image is, or the sample is pretty well learned by the currently trained model. So we sort them. We sort the newly given sample by the score, the uncertainty scores, and sample it by the constant stride to have uh, to maintain the diversity of the sample in the episodic memory. And by doing so, we are improving the accuracy over time for the continual learner on the blurry and the online setup. And also we benchmark on the offline setup and the disjoint setup. And this rainbow memory idea is working pretty well in many different type of setups. So we think that it's pretty useful to report it in the community. So we published this to the last year CVPR conference. And this rainbow memory, in this rainbow memory paper, we given the idea of using the uncertainty to score the samples and just get them with the constant stride. But this is not the only way to make the memory rainbow-wise, rainbow-fi, right? So we can use different idea to diversify this data in the episodic memory, and we are preparing the next version of diversifying the data in the episodic memory using different ideas. Yeah, all right. And we are thinking also that this blurry setup I talked about earlier, the blurry setup is less challenging in terms of the forgetting because we are seeing the classes over and over again as the task boundaries are blurry. So the other some classes are overlapping each other in over the tasks. So this setup is less challenging than the disjoint, and some people is blaming that this blurry setup may be realistic, but it is less challenging in terms of forgetting. So we have to benchmark our continual learner in more challenging setup, which is the disjoint setup, and that is one claim that makes perfect sense to me. So I try to balance between two because the blurry setup is still realistic, but it is not challenging enough for the forgetting's perspective. So I make two sections of or the two partitions of the classes. So one partition is designated for given as a disjoint setup. So we guarantee some of the classes of out of given classes. So some of the classes are given to the model in a disjoint manner, which means that we guarantee these classes are not overlapping over the classes, so that we guarantee this portion is having a high forgetting. And some of the classes, some set of classes, the other partition is used for the regular blurry setup, so that we can still maintaining the realistic setup, but we also guarantee there is certain classes are introducing newly to the model. So in the blurry setup, we have a notion of major class and the minor class. So the major class are regarded as in the disjoint setup, the major classes are the classes are given to the model at that task, right? But in the blurry setup, we have this major class, which we can sample the data from these classes, these major classes by certain portion. If we say blurry 10 setup, then we are sampling the data from this major class by the 90% of the chance. But the other 10% of the sample will be drawn from the other classes, which we call minor classes. And because of the sampling strategy, all the samples from all the classes are coming at the very beginning of the task. So there's no, new task and new classes are introduced usually. I mean, there's a chance, but it's not guaranteed. So we have this guaranteed new classes introducing by introducing a new setup called iBlurry, which we call incremental, which we mean incremental blurry setup. And on this setup, we are also proposing some baseline to tackle this setup, and we show that it's pretty performing well. And we think that it's pretty useful to report it in the community as well. So we published this in iClear this year. And if you see this setup that the data supervised by human annotator on the fly to the model in a realistic continual learning scenarios, this oracle, the human annotator, will have some fatigue and they will make some, errors, right? So as a last setup, we have talked about this, the case that the stream data may have wrong labels. So we called it noisy um, blurry setup. And in the noisy blurry setup, we have introduced a new ideas to tackle this noisy label that is given as a blurry task boundaries. And we think that is pretty useful idea to tackle more realistic setup that the human annotator will make mistakes, right? And we present this idea to the CBPR this year. So I will, so in the spring talk, I didn't mention this idea pretty solidly. So I try to, address this problem much more deeply today. And then going to our main topic of systems perspectives, continual learning problems. So the real world data has a lot of noisy labels, and this data set of animal 10N, the N denotes for the noisy, the real world data, and food 101N and clothing 1M itself and web vision, they are really the real world data that has natural noisy label by relabel them and see how much the label is actually noisy. And this table shows that this clothing 1M, which has the 1 million training points, and they have this 14K of validation and 10K of testing data, and they have 14 classes in it. And surprisingly, the real world data has a 38% of the labels are wrongly labeled, wrongly annotated incorrectly, right? And the web vision data also have large scale, also is a large scale data set, and they also have like 20% of the annotation is incorrect. That was surveyed by this paper. Yeah. And we try to use this our own idea of diversifying the samples in the episodic memory. But if you try to apply this idea of enforcing the diversity on the wrongly labeled data, then you will get the wrongly labeled data as a most diverse images or most diverse data points because they are looking very differently because they are wrongly labeled, right? So if you think about this ugly duckling story, then if you try to diversify the sampling, right, then you will choose this one among all the ducklings, isn't it? Because they are looking very different. So it is actually messing up the diversity, and it is actually messing up the entire systems very adversarially. But I mean, we know that we have, observed that this diversifying samples in the episodic memory are helpful for the continual learner, but we cannot just diversify by hindsight of the labels because the label may be incorrect. So we propose this idea of cleaning the label first, and then use the clean the label for the diversifying the samples in the episodic memory. So we have these two parts. The episodic memory construction part, we use the cleaned up label, and the second part we use the samples in the episodic memory by additional cleanup or treat them in a different manner to get the high performance by diversifying, and at the same time we clean up the label of the maybe incorrectly given labels. The first part, when we construct the episodic memory, we define a new scoring function by the purity and the diversity terms. The purity is given by the loss term that the sample that is sample. I mean, I have to use this. Yeah. So if the sample is given to the currently trained model and the loss is large, that means we think that the sample is pretty noisy in terms of the labeling. Because if we think that the sample is pretty having a high loss, meaning that this sample may not be trained well enough yet. At the same time, this sample may be having a noisy label. So we have this purity terms in the scoring function, and also we have another term called diversity, that the average, we by computing the average cosine similarity of the embedding of the same class samples in the memory. And if the similarity is large, that means we think that the samples are pretty diverse enough. So by using these two scoring functions of quantifying the purity of the label and the diversity of that class, then we use this scoring function to sort the sample, and then again use the constant stride to sample the data to be included in the episodic memory. So we use this episodic memory construction method to uh, get the first amount of the diversifying, but at the same time purified samples in the episodic memories. Once you have this episodic memory samples, oh, sorry, and we have this one hyperparameter called alpha k that balances the diversity and the purity. So we basically update the memory by the dropping a single example with the largest scoring samples when adding a new samples in the data stream. So using this scoring function um, to sample the data at the first task, and when the new task is coming, then we drop the samples with the largest scoring samples in the episodic memory and replace it with the newly added sample in the data stream. And this uh, scoring function is having a different behavior by having different balancing hyperparameters of the diversity and the purity. So we studied this effect of the alpha k, the trade-off between the purity and the diversity. And um, it turns out that having a pretty small coefficient, I mean, it is expected, having a small coefficient of the alpha, then we having a high emphasis on the diversity, right? Sorry, the small value, then we have the high emphasis on the purity. Then the memory purity is pretty high, but the diversity is pretty low. But if you're putting the high value on the coefficients alpha k, then we are having the high diversity as opposed to have a low purity things. So we get this good tables and just having zero point 0.5 as a designated value for the alpha k, right? Yeah. So that's it. So then we are using this alpha k as a soft selector to choose between the purity and the diversity. And we find that this purity and the diversity should be also a function of the loss function, because as I said before, the purity and the diversity is a function of a loss function, meaning that if the loss value is pretty high, then the sample is not yet trained well, or maybe it has a noisy labels. So we balance this thing as by setting this alpha k as another soft selector by defining it as a function of a loss function as well. So if the loss value for that sample is pretty small, then we have a high um, emphasis on the diversity. And if the loss value is pretty high, then we have a high emphasis on the purity side, right? Because that this sample may be less trained yet, or having a noisy label there. So we define this hyperparameter automatically balanced by the loss value for each of the sample. And this scheme is uh, having this scheme balancing the trade-off between the purity and the diversity well in the empirical study that we have. So we, additionally propose this dynamic balancing schemes for the purity and the diversity terms. And once you construct this memory by using this new scoring function, we are having another scheme to use this sample in the episodic memory by partition them into three different groups. So the first partition is a clean set, which we believe the samples are having a correct label. And these clean sets are usually defined by the sample that has a pretty low loss value. So if the loss value is very small, that means these samples are well trained. At the same time, it may have a correct labels, right? So we use this sample that have a pretty low loss. Uh, we believe these samples label as a correct label, and we name it as a clean set. So we just believe the given label as a true label. And if the sample is not partitioned or not categorized by the clean set, then we call this as a noisy set. And we further classify them into the super noisy set or the mid-level noisy set. If the sample is mid-level noisy set, then we try to clean up this label by the relabeling schemes that is around in the robust learning literatures. So we use one scheme called um, divide mix to clean up the label. And we relabel these middle level noisy samples by using these already existing schemes. And if we think that samples are having really noisy label and we cannot even have a chance to clean up the label, then we just detach the label and use them as an unlabeled sample and use it as a representation learners. Yeah. So we partition the samples in the episodic memory. Even though we try to clean up at the construction phase, we try to further clean up to use them in a separate different partitions of the clean set and the noisy set and the noisy uncertain set. Okay. So make sense? Yeah. So using these two parts of the idea, we compare with the previous arts with combining the noisy cleanup method, because it's too unfair to use the previous method without cleaning the label, because we know this samples are having the noisy label, and the straightforward approach is to combine the label cleanup methods before we apply to the many different continual learning methods, right? So we combine the previous continual learning method with the label cleanup methods of selfie and co-teaching and divide mix, and compare the performance with our proposal called Puridiver. It's called Purifying and Diversity Episodic Replay method. And comparing to the other methods, our methods are having pretty good gain over the state of the art, but uh, and we are also benchmarking the two different scenarios of the symmetric noise and asymmetric noise of 20% and 40% and 60%. And 60%, you mean that more than half of the samples are having a noisy label. And in this very challenging setup, our methods are having a big gain as opposed to having a small gain in the pretty clean label setup, right? And this RM is our own baseline, our own state of the art. And you see the gain is not much in the smaller noisy setup, but as the noisy portion is increasing, then the gain is also increasing. Yeah, so we also do some evaluation study of using uh, uh, the sample usage strategy in the episodic memory, in the sample of the episodic memory, and using the R set and U set. The R set is a relabeled set, and the U set is a unlabeled set, meaning that we are having a no hop of this incorrect label and use it as a representation learners, right? So using the R set and the U set in the noisy setup, then we are having bigger gain, larger gain by using either of them. Okay, so we have to use both to improve the accuracy further. And it's pretty significant differences over the other counterparts. And also we have this adaptive alpha uh, balancing strategy. So as opposed to having a fixed alpha k value, the adaptive alpha having a better gain over the other fixed values on many different symmetric noise ratios of one data sets. I believe this is a CFAR10 data set. And also, this is coming from a reviewer's comments, and they're asking us that whether your new methods are having a high computational cost, but it turns out it's not much. So, comparing to the other state of the art that combines with the noise cleanup methods, our method does not add much more computational cost, but having a big accuracy gain uh, compared to the other baseline that is combined with the other, you know, the label cleanup methods. All right, to summarize, the sample diversity in noisy label needs to be reconsidered, but still the sample diversity matters once you have a cleaned labels, right? Even though you are having the noisy label stream data. So our idea is to partition the labels by the three sets and treat them in different manner when you're using the samples in the episodic memory. But when you're constructing the memory, we also even consider how to get the samples with the most cleaned data from the noisy annotators. So the code is given here, and you can download and try to reproduce it. And if it's not reproducible, then please let us know, and we'll fix the bug. Uh, for your reproductions. So any questions so far? No?
I have a few, but would you rather me ask now or wait till the end?
You can ask now. Yeah,
Okay.
I think it's
Um,
better. Yeah.
yeah, so could you please go to the slide with the three losses?
Mm-hmm.
Or, yeah, right there.
Yeah.
Or one more past
This
that.
is two
Sorry.
losses.
Sorry, the three loss one, where it was the different, the taxonomy of,
This one?
no, sorry.
No.
It was the I guess decision tree on whether or not you do is the label is the are the labels clean, and if they're not clean, do you do
Oh, I see. I
sorry,
see.
yes,
I
yeah.
see. Yeah. Yeah. That one.
Right, oh
Yeah.
yeah, there we go. Yep.
Mm-hmm.
So yeah, I'm just wondering have you tried or considered doing contrast? I had two questions on this. Have you tried or
Mm-hmm.
considered doing contrastive loss with all of the data, or do you just do contrastive loss
Oh,
with data that's kind of quote not
that
useful?
that's very interesting question. We didn't consider to use every samples as a contrastive loss first and then use it later. And we just use the super noisy samples
Gotcha.
for the contrastive loss. But this is certainly a very interesting idea.
Yeah, it may not help. It could stabilize it. It may not help at all. I'm just this
Right,
reminds me a lot of these type of semi-supervised in a way kind of losses. Actually brings
that's
me
right.
to another question of
Hmm.
for the yellow loss, the
Hmm.
noisy relabeled cross entropy
Hmm.
loss with the relabels, did
Right.
you have to did you have to do any type of schedulizer to ease in this relabeled data, or did the alpha value or something help with that? Specifically, like I know with fixed match or some prior methods on semi-supervised learning, when they had pseudo-labeled type losses, they had some type of growing way to gently introduce them, like a warm-up scheduler.
Hmm.
Did you have to use any type of warm-up scheduler for that, or did the alpha value inherently handle that, or was it just did it work fine as is?
We use this divide mix scheduler. So we have
Okay,
to
okay,
use
okay,
this warm-up scheduler for the divide
okay,
mix,
okay.
but this alpha value is not, playing a role here. But certainly it is pretty interesting that any different types of the warm-up scheduler or incorporating this relabeling scheme into our methods and a part of the method so that the alpha value may be just taking care of this kinds of scheduling by itself. But we haven't thought about it, but we just use the
Yeah,
divide
okay.
mix as it is
Yep.
to have a fair comparison with the other method that uses divide mix as a label cleanup
Makes
methods.
sense. And these
Yeah.
seems like powerful tools to help. I just was asking because I know with some of this overlaps with some types of semi-supervised, and some of the details can get intricate there. So it's nice that you were able to build this wonderful method that you know handled all of those on a lower
Mm,
level. So yep,
yeah.
those are my two questions. So thank you for your answers.
Well, thank you. And for your first question, if we use every sample as a contrastive with the contrastive loss, that may be helpful, but we still use those samples with this supervised
Right.
loss, right? So we still have some signals for learning the representation with these samples. So I believe without using them with the contrasted loss again, we can just rely on the supervised loss with these samples and still having a similar kind of performance without using them. But that's my guess. But it's certainly interesting to see uh, how much these samples are affecting positively
Yeah.
using them with the contrastive loss.
The only thing I can think of would be if you start it with the contrastive loss and then added the label loss in. I know there's many works that have shown
Exactly.
sometimes that those type of
Exactly.
representations are more less vulnerable to catastrophic
You're
forgetting,
right.
but at that point it's probably an orthogonal to your research, so it's not very relevant,
Yeah.
I guess, from that perspective. But
It's going to be another kind of the idea. So it's going to be another method. So it's a continuous manner of scheduling the laws on the contrastive to the cross entropy for the selected samples with soft weights on that. I mean, this is very interesting idea.
awesome.
Yeah.
And that's it from me. Thank you.
All right. Yeah. Very good questions. And any other questions? If not, I'll.
Can
Oh,
I
sure.
just add one question?
Mm-hmm.
So since you relabel like as like wine had eye, so is it possible to use like something like supervised contrastive loss after you relabel it?
Oh, that's also interesting. But we just use the cross entropy as
Oh,
a vanilla loss choices. But yeah, so I mean, certainly supervised contrastive loss is maybe an option.
okay, yeah.
Yeah, cool. Another awesome question. Any other questions? Right, so if not, then I'll move on to our main recipe, main dishes for today. So to recap, the continual learning scenario would be very necessary in the user end devices, as I claimed before, right? So we have to consider the resource constraint scenarios with limited episodic memory and limited model size. But we only consider the limited episodic memory, and the limited model size is going to be the next work from any of you or me. And the limited episodic memory is a challenge that I faces right now. But we are thinking about this scenarios as real world scenarios, but we are not actually thinking as a real world scenario because we didn't think about the device that we can use for the user end devices, right? So when you think about the uh, device to get the data, the stream data from the human annotator, we are thinking about this memory, and I was thinking about this memory as a RAM, and we are kind of forget about the fact that we have additional storage that can supply the data for the memory, right? So if you have this memory in the system, right, in the model, then this episodic memory can be regarded as the RAM, and this RAM or if you think about this model as a CPU, then you can have this small memory as a SRAM in the CPU. Then if you have some other extra storage or the RAM, then you may have some small devices that managing the data in between the data in the CPU and the data in the memory and the data in the RAM by using the cache memory, right? So why don't we use this cache memory idea to get the additional data that can be stored in a storage, even a RAM or even in the storage, if we don't have any latency between the memory in the model and the extra storage outside of the model, right? So we can think of this larger, slower memory outside of the model that supplies the almost virtually infinite amount of data to the memory if you have no latency that swapping the data in the memory and the larger slow memory. If you really think about the continual learning as a systems perspective, right? Right. So then can we use this larger memory? Not immediately because of the following reasons. The transaction between the episodic memory and the system memory would take long time, right? So that swapping thing may takes forever, so that we are not even think about as an option for using the larger size memory, extra memory. So our proposal is to prepare the necessary data in the backend, the system memory, and update the episodic memory when system is idle. So we are actually having this carousel. Then we just provide some of the data in the carousel by replacing the horse in the carousel when the system is not using the memory very actively, right? So that's basically the idea. So we try to minimize the delay using the system's memory to the episodic memory by parallelizing the transaction between the episodic memory and the storage with another worker. So we call it asynchronous sample retrieval. So from the storage to the memory, the transaction between the episodic memory and the storage will be given as a asynchronous manner, so that the model is having no idea of the swapping in the episodic memory, because the model is not using any resource of the episodic memory when the model is idle for the retrieving the contents in the episodic memory, and then we replace it by another extra worker that replaces the information from the episodic memory to the storage and back, and the vice versa. So we call it carousel memory as like the next version of the rainbow memory. So here we have this incoming data stream called I. The stream data is enqueued to the bundle on the buffer, and we have a training stage in the using the old sample and the newly come sample in the buffer. We train the model, and we have this M stage that having the probability whether this sample is going to be used for the next time step. Using the reservoir sampling or the greedy balancing sampler, we just put these samples to the episodic memory. We move the samples to the episodic memory, and we have this R stage that swaps between the episodic memory and the storage when the sample is not used in the episodic memory. Okay, so and also we update the storage by having maybe this sample is going to be used in the time span at any time, so we just put it in the storage. And we also have this R stage that I just explained, that swapping between the memory and the storage. So equipped with the the carousel memory with the previous state-of-the-art, the BIC and dark experience replay and the rainbow memory, and we compare the baseline that called RAM-S, RAM-S that refers to the episodic memory only setup, that is a traditional continual learning setup. And we also have this baseline of the storage only that has a large size storage, but we here to compare fairly with the RAM, as we have the same size RAM that is equipped with the model to the episodic memory, but has a big latency, right? Because it's very slow memory. And we have this STL, the setup that has a storage with a no limit size, which is upper bound, has a large latency, but has a very high accuracy there. So compared to the RAM-S, the regular continual learner, if you're using the CAR-M with the 100 storage size, that compensates to the large storage size that has an infinite amount of data, we have very close to the upper bound of the accuracy with very small latency. So here, the latency is here. The asynchronous is meaning our CAR-M, the carousel memories, carousel memories overhead in the training time. So the minus is actually the decreasing training time. And I mean, this minus is actually marginal because it's just, having a small different training schemes or the initial points. So the minus 0.3% is just regarded as the same time span for the training with and without the memory, the extra storage memory. And we compare the asynchronous and synchronous manner of the training time increases. if you're using the synchronous manner of training, synchronous manner of the swapping between the storage and the memory, we have significant increase of training time. But if you're using the asynchronous manner of updating the episodic memory from the storage, we have a virtually zero training time increases, as opposed to have a pretty big gains of the accuracy that is close to the upper bound in many different state-of-the-art continual learning methods. Okay. All right. So here, what is this? We also compare with the different episodic memory size because of the fact that if the episodic memory size is sufficient, then we don't need to have this additional storage, right? But even if we are equipped with the larger episodic memory size, we still have a larger, even larger storage outside of the episodic memory. So still there's an accuracy gain with the constraint that the episodic memory cannot be larger than excessively larger than necessary. And also we change this data swapping ratio to reduce the overhead of the asynchronous worker. Also, we vary the size of the storage capacity outside of the episodic memory to compare the accuracies. And we also try on the real device by using the NVIDIA Jetson TX2 on CFR10, and by actually deploying to the edge devices of the NVIDIA Jetson, even though it has a GPU in it, it's still pretty lightweight devices. And our method, the CAR-M, is having a significant gain compared to the setup that only uses the episodic memory without having without regarding the additional storage size. All right, so I have two key takeaways from today's talk. We have presented this new continual learning setup and more to come in the next conferences. And the second takeaway is to remember is that we have to remember that the continual learning method would work in a system. So we should not ignore the existence of the system memory, or we should not ignore the other existing components of the system that we're gonna deploy our continual learner to the real world data, real world devices. So we have to always think about the real world continual learning deployment scenarios, because the continual learning is motivated by the necessity of deploying the system to the real world devices on the stream of data that is annotated on the fly or other scenarios. So we have other ideas to come from my groups. So stay tuned, and I really hope that I will give another talk in the Continual AI's YouTube series in the next future. All right. Thank you very much. And if you are curious about detail, please come to our website. And here are my collaborators, amazing collaborators to make these happen. Thank you.
Well, I'm
I'll take
excited to see
questions.
what you solve next, because I was honestly felt very refreshing that last part of your talk,
Right?
and that kind of really connected a lot of the dots. And we have people talking about we have constrained memory and continual learning, but sometimes the numbers seem kind of arbitrary.
Exactly.
We always talk about connecting these settings to real world devices, but it's not really
Hmm.
done. And then there's also
Right.
people talking about this long term memory, short term memory, but it's more
Right.
focused on, you know, where people seem to be motivated more by, natural, neuro inspired, where, I think a big takeaway here is right now, device
Right.
inspired, what's
That's
going to
right.
work
That's
there.
right.
And, I thought that was really great talking about the idea of, if we're trying to efficiently continually learn, the way the
Hmm.
device is going to be set up is having this, RAM versus the, memory versus storage are two different things, and taking advantage of that as you start in this introductory work, has tremendous real world implications. Um,
I think so. Yeah.
that's and yeah, and I'm, my main question, I guess, is, and you don't have to give too much of your next work away, but where do you think is the big to me, I think there's two kind of fruits that come from this last thing you talked about. You could either work really hard on the communication between the two memory types and getting the data set up. And another
Right.
thing you think about is, hey, with these two different, you know, there's two different memory streams now. This has now changed our loss functions and how we want to, do long-term, like change the optimization, like having two different trajectories in the optimization. So I'm curious from your perspective, do you think these two are equally important? Do you think one's more, more inviting right now? Or if you have any comments on that, that'd be wonderful.
That's a terrific question. And I think these two different data stream, one from RAM and one from storage, may need to be treated differently because the data from the storage is having no regulation to be added, and we need to have some certain different criteria to be used for the computation of the loss, as we have talked about this Puri diver thing. And the sample that is included in the episodic memory is more it's more regulated way of sampling from the data stream. So we may just treat them as a trustable source of data to be computed for the loss function. So I think that they need to have a separate, different, loss function design for the two different data stream. But let's see whether we just having one single unified loss is taking care of everything, and having the marginal differences between two ideas. Yeah, but that was a terrific question. We certainly need to think about it.
I hope you noticed that Watson decided to come join for the last part of his
Yep.
talk.
Yep. So I've noticed that he or she
He.
he is just wandering around and just sleeping.
He goes where he wants.
Yep.
Does he want to sleep on this bed or sleep on a different bed?
That bad, right? That's
Were there
great.
any other questions, Elaine?
Sure.
I see
Yeah, I'm happy to taking them.
we can take one more.
I have one question.
Sure.
So since you consider like system memory, so are you considering maybe using like a smaller architectures, like not ResNet, but like a mobile net, or to kind of create more memory space for the episodic memory? Or
that's another wonderful question. So I was talking about this limited episodic memory so far, and I haven't tackled about the limited model size yet.
Okay.
So this is going to be the next big research venue that you guys can work on.
Okay.
Yeah. So I just let you work on and just make another challenges over that. I'm also working on that too. But,
okay.
Welcome more ideas to come for this new setup for the limited model size as well. Because, as I said before, the continual learning is the setup that is shooting for the real world scenarios. So we have to think about we have to really push ourselves to get the real world continual learning or the real world AI system to be working. And one quick advertisement is that in the Puri diver or iBlurry setup or the blurry setup or disjoint setup, everything needs the definition of a task, right? So they are having a discrete definition of a task that has some small set of classes in it, right? But that is really unrealistic, isn't it? So we don't have any definition of a task. We just only see the stream of data. So my next work was to tackling the continual learners on the continuous data stream without the notion of the data, without the notion of the task boundaries. So here we have very big challenges because all the measures that we're evaluating on, like the forgetting or the intransigence, and these kinds of measures requires the definition of a task. So over the task, what is the accuracy drops, right? What is the accuracy increases? So here we need to have a definition of a task to compare with. Yeah. So,
and also I almost think of federated learning types things where you could think of random samples into that some type of convergence, and it's all converging together now. But
that's right.
Yeah, that's
important. But that haven't addressed it yet in the continual learning literature.
No. Yeah.
Right. So here
we have sounding kind of closer. The two things are
exactly. So here we presented new, continuous stream of the data, continual learning setup, and it's in the under review. So you can see in the open review by, typing this similar kind of thing. And I believe this is a pretty useful directions to go. So we are also shooting for the new setup and also propose a new methods on that new setup and try to push ourselves to get the continual learning model that is actually useful for the real world scenarios. Okay,
Great. I think this is a great time to wrap up. Thank you
sure.
so much, Jong, for this second presentation you give us. And as you mentioned, we hope to have you again.
Yeah,
Talk about more how
tremendously
this goes.
happy to give more talks in here.
Well, to everyone listening, you can join us back at our regular time next week. It'll be our last installment for 2022. We will hear from Camila Gonzalez discussing task agnostic continual learning on hippocampus segmentation. So it
Mhm.
should be a really exciting way to finish off 2022.
Yep.
Hope to see you
Task
there.
agnostic. As I said, this is very important topic.
Yep.
Yeah.
Thank you,
All
everybody.
right. Yeah. Thank you very much to having me.